Let's go through Activity 7. And actually, first thing I want to do is go through question number 3. It's nice and short, and it deals with support vector machines. So let me go ahead and just run the lines of code all the way down until plot and describe this problem. So here we have our data space, basically all possible combinations of the x1 and x2 characteristics for the individuals that we have data on. And the idea behind a support vector machine is to find some sort of separating hyperplane. Now, in the original data space that we have, it's very obvious that a separating hyperplane doesn't exist because no matter what line we were to draw that bisects this space, there's no way that all of one class is going to be on one side and all the other class is going to be on the other side here. So the idea of the support vector machine is to project the data into a higher dimensional data space where there may be a separating hyperplane. So what does projecting into a higher dimensional space mean? Well, it just means adding in additional variables to your data set, basically derived variables that are some function of the variables that you have collected. So in this case, what we're going to do is add in a third dimension to the data frame here, a third variable. And specifically, the value of the third variable, I'm just going to call it x3, is just going to be the sum of the squares of the two other variables we have. Basically, x1 squared plus x2 squared. So what is this doing? Well, x3 is essentially measuring how far the individual is away from the origin of the plot, the point 0, 0. And we can see that that's actually a smart additional variable to add because it looks like the red class is all at about the same distance away from the origin. The black class is much further away. So this additional variable should allow us to increase our method's ability to classify. All right, so let's load up library RGL, which will allow us to make a three-dimensional plot. So let's plot this now three-dimensional data space after adding in this third variable, color coding the points by what their classes are. So you've seen as soon as I've done this that we have successfully found some sort of separating hyperplane. If I were to draw a plane that bisects the space right here, all of the black class is up on top, all of the red class is on the bottom here. They're really separated really by quite a large margin. So this addition of this new variable, basically the distance away from the origin, was the key to separating these two classes just with a hyperplane, kind of a flat plane here. And so support vector machines attempt to do that. Now the way they actually go about doing that is really weird. They use a mathematical trick called the kernel trick and actually just define the similarities between individuals without explicitly actually defining new variables to project the data into a higher dimensional space. But the net result is essentially the same. Very often this technique just works. It is able to find a separating hyperplane in a higher dimensional space. All right, now let's continue with question number 1, where we re-examine the churn data frame and see how well various models can predict whether customers do or do not churn. So we're going to load up the churn data frame and we're going to split the data into the training and holdout samples, much like we did in the last activity. Now here is how the previously considered models do on the holdout sample in terms of the misclassification rate. The misclassification rate to beat is with the naive model, the majority class, which is 13.6%. Now, the majority of people in the data do not churn, and so by sheer virtue of numbers, it looks like we're going to have a naturally low misclassification rate. We need to make sure that our model is doing better than the naive model. So let's start with a random forest model. Now, just like the name suggests, there are a lot of components to a random forest model that rely on randomness. So in order for us to reproduce the same result more than once, we basically need to be presented with the same sequence of randomness each time. So we're going to be setting the random number seed to 474 every time we run a random forest so that we can all get the same answers here. Otherwise, there's no way I can check to see if you've run your code correctly. We come up with different models and different answers, etc. All right, so we're going to run random forest using the default parameters here. I'm going to save the result of running the random forest to just forest in all caps. The way we specify a random forest model is similar to the ways we specify the model in all the other ways we've looked at this. Basically, we say the name of our variable we want to predict, churn, and then twiddle dot to predict it from all of the variables in the data frame. and we'll say where this data lives. Now, it's important that we always say that it's on the training data. We're saving that holdout sample to the very end to see how well we generalize to new data in actuality. All right, so before running that random forest, we want to make sure to set the seed to 474 and always run these two commands as a pair. This way we'll all get the same sequence of randomness. We'll all come up with the same result. All right, so let's find the error from generalization error from reg class. So we're going to look at the generalization error of our forest model on the holdout sample. Now, if we run this, we get a bunch of other things like the confusion matrix. I'm going to extract just the misclassification rate by doing $holdout. All right, so we can see that the random forest model, 4.08% misclassification rate, is doing much better than the other models, but just a little bit better than the partition model, the vanilla partition model. We'll revisit this in a second. All right, well, let's try a few different random forest approaches here. This was just with the default parameters, the default value for mtry, the square root of the number of predictors, and using 500 trees. All right, well, what about if we upped the mtry parameter to ncallTrain -1? Well, if we do this, that would employ just pure bagging at this point, because at this point, we would be trying out every possible predictor in the training data to base a new rule on for each tree in the forest, and call -1 because one of the columns is the thing we're trying to predict here. But let's see how well this does. People have studied this, and typically just bagging all by itself does not give a model that performs as well as if you give a random subset of predictors each time you choose a new rule. So let's see, did we do any better? Well, no. We actually did a little tiny bit worse, going from 0.04 to 0.044 here. So trying out all of the columns each time you want to add a rule to a tree in the random forest, typically not what you want to be doing. That's why we pick a random subset. And finally, what we're going to do is to rerun random forest with just a smaller number of trees. So we'll replace the mtry with ntree. Very important that it's not pluralized. The important thing about a random forest is that we have enough trees that we're averaging together. Now, it's always fine to have more than necessary, but if we don't have enough to average together, our prediction might be relatively unstable and inaccurate. So we might be curious to know, was 50 trees enough in this case? So we'll set the seed, run the forest, and see what the generalization error is. And in this case, we actually do better than with 500 trees. That's just a happy accident. The more trees, the better it is overall. It just so happens to be the case that the 50 trees that it first built look to be, particularly good generalizers of making this prediction here. All right, so question B asks us to compare the random forest model with the vanilla partition model, this misclassification rate of 4.64%. We found 4.08% using the default parameters. Now, because the random forest model uses a lot of randomness, it kind of begs the question, all right, well, which random forest model are we really talking about? If we switched up the random number seed, we would have had a different random forest and a different set of predictions and a different misclassification rate on the holdout sample. So why don't we look at the results from a bunch of different random forests just to see how variable their generalizations are on the holdout sample, to see whether or not we actually believe in this case that the random forest procedure is doing any better than the vanilla partition model. So what we're going to do is we're going to look at 100 different random forests and see what the possible errors we observe are on the holdout sample. All right, so what I'm going to do is just to define a vector called errors here. That start out to be blank. I'm going to store the misclassification rates on the holdout sample one by one as I go through each forest. And then what I'm going to do is I'm going to loop through a value of I in 1 to 100, the integer sequence, representing basically what tree number I'm currently looking at. And what I'm going to do is just borrow the code that I have up here, fit the random forest on the training data, but using a value of ntree equal to 50 here, which is what's suggested in the problem, not setting the random number seed ahead of time so that I'll get a different random forest model each time. And then what I'm going to do is to put into the ith element of my errors vector what the misclassification rate was on the holdout sample. All right, so we'll go through this procedure 100 different times, and what we'll do is we'll look at a histogram of the generalization errors that occur on the holdout sample, and we can compare kind of the distribution with the vanilla partition model's misclassification rate on the holdout sample, which is 4.64%. So once this is done, and it'll take a while because it is running 100 different random forests here, we can look to see, all right, is the random forest procedure just better as a whole than the vanilla partition model? Now, sometimes when we run the random forest, we just happen to luck out and do better than other times, depending on what trees happen to be generated. But over the course of 100 trees, we see that or 100 different forests, we see that the misclassification rate on the holdout sample is very convincingly below what we found for the vanilla partition model, because the largest we see is just a little bit above 4.4%. So the largest misclassification rate we see on the holdout sample from any of these 100 models is just a little above 4.4%. So we are convinced that the random forest procedure is better than the vanilla partition model in this case. That's kind of the hard thing about talking about a random forest, is it's basically begging the question, well, which random forest? Rerun the procedure, you'll get a different model out and different predictions. But as a whole, it looks like the procedure is quite sound. It's doing better than the vanilla partition model. All right, let's move on to boosted trees, basically fitting a sequence of very, very simple trees, each trying to improve on the results of the last. Now, the author of GBM insists that we recode what we're trying to predict as a 1 and a 0. Kind of an annoying thing, but we just have to play by the rules. So what we're going to do is to copy the original training data into a data frame called train.gbm. We'll use train.gbm to use in our boosted tree model. All right, so what we'll do is we will take our churn column here and convert it into numbers. Now we can use as numeric to do this, but if we do as numeric on a factor, that changes the numbers to 1, 2, 3, 4, etc., whatever the levels are in alphabetical order. If we want ones and zeros, we need to subtract 1 off from all the results. So I'm going to do as.numeric, and this way a 1 will be a yes, a no will be a 0, and we can go ahead and fit the boosted tree. So I'm going to call the model GBM here. The command is just GBM. The formula is set up just like every other formula we've talked about. We're going to churn twiddle dot, predict churn from every variable in the data set. Specifically, the training data set, we're reserving the holdout sample till after we're done here. And what we're going to do is to run this with the default parameters here. All right, now the other important thing is that by default, the GBM procedure in R actually performs a little bit of bagging, meaning each tree in the sequence works with a slightly different version of the training sample, and it's generated kind of in the same bootstrap procedure as what the training samples in the random forest procedure see. And so the important thing will be that we actually also set the random number seed before running GBM so that we get the same sequence of trees so we can compare results here. All right, so I'm going to fit both of these, or run both of these lines. And there's already an error here. Why is that error? Well, guess what? I'm passing it the training data, not the train.gbm. Train still has churn as yes and no. It needs ones and zeros. So there we go. All right, now we're going to make predictions with here and find the misclassification rate on the holdout sample. So what I'm going to do is to type in predict, the name of the model that we're using to make our predictions, the new data, which is the holdout sample, and then I'm going to play around with a few arguments I can add to the predict function. So what I would like is just the class prediction here. We're classifying into yes and no. Sometimes we get to do this, sometimes we don't. If we add in type equals class and then try to run this command, all right, well, we're asked for the number of trees used to build the model. It's 100 by default. I was got to make sure those two numbers match up. If I do this, I get an error that says, all right, my only two choices are link or response for what I'm predicting. Response in that case is what I'll do. If I look at this, these are all the probabilities that the model is predicting for each of the classes here. So what I need to do is basically convert them into yes and no's. So I can use that if-else statement here, basically go through each element of the result of running this command here, this vector. And if that is at least 0.5, we're going to make that to be a yes. Otherwise, we're going to make that to be a no. So now if I run this, we get a whole bunch of yeses and nos here. Well, the first few are just all nos. And what we're going to do is we're going to save that to just a vector called predictions. All right, so what's the misclassification rate? Well, here's a shortcut. What I'm going to do is I'm going to say predictions not equal to holdout $churn. What is this doing? Well, the predictions are for the predicted classes on the holdout sample. Holdout $churn are the answers on the holdout sample. So if I ask whether or not predictions are not equal to holdout $churn, this will evaluate to a true if the answers don't match up. In other words, I made an error. And it'll equal to false if the two values are the same, meaning the model got it correct. Now, since true is 1 and false is 0, I can ask for the average of that vector, and this will give me the misclassification rate. So this is the misclassification rate. Let's run it. 13.6%. Terrible. The worst we can do, it's the same thing as the naive model. The default parameters in GBM rarely are the ones you actually want to be using. In fact, in this case, if we look to see, all right, we actually just predicted everything to be no here. So we do need to do some sort of tuning. We can't use the boosted tree right out of the box. You have to figure out a good number for the number of trees, the interaction depth, the number of rules that you use for each tree, and then also the shrinkage parameter, the rate at which the tree is learning. So let's try a whole bunch of these things and see what seems to be working good. I'm going to borrow this code and just update what the parameters are that we're going to use for the models in question. So I'm going to add in additional arguments here for GBM, n.trees of 100, interaction depth of 1 rule per tree, shrinkage of 0.001. Very slow learning tree. Slow learners are typically better. And we're always going to set the seed right before that and run that as a pair. All right, so 13.6%, terrible. That's basically the naive model. This was the default values, I think, of the GBM, just showing that, all right, if you just do it with the defaults, they're going to come up with a really bad model typically. Well, what about if n trees is 5,000? Well, what happens if we add in more trees? Got to make sure our predictions and the model uses the same number of trees. Let's see if we do any better. It takes longer because there's more trees. Eventually we'll get an answer. While we're waiting, I'll go ahead and do the next command here, where basically we take the shrinkage parameter and make it a little bit smaller, make it a little bigger, make it a faster learning tree. All right, so 5,000 trees, but with the defaults for interaction depth and shrinkage. Oh, we're doing a little bit better. Not that great though. We've seen 4% misclassification rate here, so let's keep on tuning. What about a shrinkage parameter of 0.01? Is that any better? Well, we can run it through and see how we do on the holdout sample. Very quickly, we're going to learn how to do this tuning efficiently, so we're not doing this manually. All right, looks like a larger value of the shrinkage parameter made us do a little bit better, smaller misclassification rate. Well, okay, what about a larger tree at each sequence here? 2 rules per tree with a shrinkage parameter of 0.001. Is this parameter set good? Well, let's find out. Looking forward, it's the same stuff, just with a 0.01 here. So it looks like that is actually a key. Instead of having each tree in the sequence have just 1 rule, it looks like we actually want 2. Pretty big increase in accuracy here. The misclassification rate's much smaller. Do we do any better by increasing that shrinkage rate, like what we saw when we used that interaction depth of 1? Maybe is this a better set of parameters? Wow, even better here. Now we're approaching essentially the misclassification rate of the vanilla partition model. The random forest was still doing better. So, all right, if we keep pursuing this, maybe if we increase the value of the interaction depth, the number of rules per tree, we do even better, going from 2 to 3. Now taking the shrinkage back down to 0.001. Let's run it. I'm going to copy and paste again. We're also going to look at a shrinkage of 0.01, and we'll see what ends up doing better. And this is what we do when we're building a predictive model. We're basically trying out a whole bunch of different models and just seeing what looks like, generalizes well to new data. There's no set recipe for basically what the parameters need to be, so we just got to try out a bunch. All right, 0.0488, a little bit worse than the last one we tried. What about 3 rules per tree, but a shrinkage of 0.01? Maybe this will be the best of all. We'll find out shortly. The carrot package, which we're about to talk about, does all of this tuning for you. We'll go through all the combinations we're interested in looking at and keep track of which ones seem to be good. All right, so 3 rules per tree, shrinkage of 0.01. We're doing better than all the other ways of building this model that we've seen before. So we could continue this and just kind of go through even more parameter sets to try to find one that does even better, but typically the philosophy of predictive modeling is we find one that seems to be acceptable and just go with that. The model with the lowest estimated generalization error is very rarely the one that ends up predicting the best on a true holdout sample anyway. But we've tried a bunch of different models and we see that their performance can really differ depending on what the tuning parameters of those models are. We got to be careful in how we build the models. All right, now let's try out the support vector machine here. And to do that, we need to make sure that every single variable in our data frame is numerical. So we're lucky because the churn data frame only has 2 categorical predictors, international plan and voicemail plan, and they both have just 2 levels here. So we can just convert those factors into ones and zeros. So something very similar to what we did with the GBM, converting the churn column to ones and zeros, we're going to convert the international plan and the voicemail plan to ones and zeros. Now that we've done that to the original data, we'll go ahead and split that into training and holdout the same way we did before. And let's try out the support vector machine. All right, we need library E1071, and the command is SVM here. The formula is the exact same formula that we've been using all along. So it'll be churn twiddle dot, predict churn from everything from the individuals in the training data. And we need to specify what kind of kernel we want. So we're going to say kernel equals linear. We're assuming that a separating hyperplane exists in the original data space. Let's see if that's reasonable. We can fit the model. Now we can get our predictions out just by using predict SVM on the new data equals holdout. What's nice about this is that the SVM by default makes yes and no predictions. All right, so we've already kind of seen how poorly it's going to do. If we look at the holdout error rate here, take the mean of predictions not equal to holdout $churn, that's going to look at the fraction of values that are different, the misclassification rate, and we see that, oh, this is basically the naive model. Not so great. All right, well, what about a different kernel, a different way of approaching the problem? Let's try a polynomial kernel here. So projecting it into a higher dimensional space by adding polynomial terms of the originally collected variables. And we're going to make this a degree 3 polynomial, like a cubic polynomial, with a cost of misclassification of 1. All right, so is this way of doing the support vector machine any better? Yeah, made a big difference here. The misclassification rates dropped to 6.24%. Not as good as those tree-based models as we've seen, but hey, we're on a roll here. Why don't we try the cost parameter of 10 instead of a cost parameter of 1 to see if this happens to work any better. Sometimes it will, sometimes it won't. Comparable performance, maybe a little bit worse here. Well, one more kernel. Let's try the very famous, very popular radial basis kernel. This one projects into an infinite dimensional space, a lot of freedom to find a separating hyperplane, and very often this works very well. Let's give this a cost of 1 and see how well we do. 6.64%, and so the polynomial kernel did a little bit better, but we could always tune the cost parameter. Maybe that would get a little bit, make a better performing model. But anyway, we have a few examples of how we go through all these different advanced classification schemes.